the last class, we saw more about how the DC motor actually works, and when you are going to combine it with some sort of load, how do you then determine how or where the system will operate, at which speed it will run. So that is then determined by this intersection between the speed versus torque graph of the motor and the speed versus torque graph of the load. Where they intersect, that is where the system together will operate. So when I say load, it is everything that is going to be there on this side. In this case, what we have drawn is a simple fan, but in general it may not be so. It may be some series of mechanical linkages connected with something else. It could be as sophisticated as one can look at it, but the entire thing, how it looks like to the motor, is this represented by this graph, and as far as the motor itself is concerned, that is represented by this graph, and therefore where they intersect is where the system together is going to operate. Now, as I mentioned, that there is a certain maximum speed of the motor, maximum current and maximum voltage. Those are the limits of operation. But when you look at electric motors, the operation of electric motors, in this case, we considered that if you look at the stator, we have a magnet which is going to produce a magnetic field, and here you have a magnet that is going to produce a magnetic field. So as I mentioned, one point, this face of it, if it represents north, then this would represent south, then this would represent south, and this represents north, and this is then the outer circumference of the stator itself. So the field lines will then come out of this face, go into the rotating member, that is armature, and then come out of this. There would be field lines that form a path here, and then there would be field lines that will form a path here. So this is the way it is going to go, and as we said, in this particular case, there is no way you can adjust the strength of this magnetic field, because you have a fixed magnet. There is no adjustment that you can do to it. It will generate whatever magnetic field will happen. Right? There is no adjustment that you can do. But there are machines where this is not the situation, and what you have is, let us say, the outer surface looks like this of the cylinder in sectional view, and then what you have is a structure that roughly would look like this, and similarly a structure that would roughly look like this, and then you have the inner surface of the cylinder, and then you have the rotating member sitting here, that is the rotor. Right? So here, if you want to generate a magnetic field, what you can do is shoot several turns of some conductor, bring this out, put several turns of conductor here, bring this out. These two you simply connect in series, so that whatever current you send here will be the same current that will flow through this, and you can connect a DC source here. Now, because you have a flow of current in a loop, this then will be able to generate a magnetic field. So you can arrange the direction of flow of this current and the winding direction in this such that the magnetic field in this will flow out of this into the rotor and then flow here, back through this, and then forms a loop here. So this may still look like north, this may still look like the south pole as far as the rotor is concerned. So these sort of machines are called as wound field machines, whereas these kind of machines are known as permanent magnet machines. These are sometimes called PMDC machines. These are simply DC machines, wound field DC machines. So obviously you can see that the mechanical arrangement is a little more involved in the second case, and this machine will therefore be bigger than the other one, which is quite obvious from the figure. But what is the advantage you get? The advantage is that the strength of the field that is generated in the second case can now be adjusted by determining how much current is there for the field. The armature part of it, whatever is there in the rotating member in both cases is the same. There is no difference to that. The only difference is in the second case, you are able to adjust the level of magnetic field, whereas in the first case, you cannot adjust the level of magnetic field. Why is this important? We said that if the rotor is going to rotate with a speed of omega, here also you have a rotor that, let us say, rotates with the speed of omega. Some classes ago we said that there is an induced EMF which is going to depend upon speed, and it depends upon the strength of the magnetic field. Now for a particular design of the armature, when it has a certain number of electrical conductors connected in a certain fashion and so on, as the speed is going to increase, the induced EMF will obviously increase, and the machine is designed to withstand a certain maximum level of voltage, and the induced EMF is going to be simply proportional to B multiplied by omega, right? So as the speed of the machine increases, the induced EMF increases, and at a certain value of speed, it will equal the maximum voltage that the machine is designed to withstand, which means you cannot go beyond that value of speed for operating the machine. If magnetic field is kept the same, right? So in the first case of the machine, there is no way to adjust the magnetic field, and therefore that decides what is the maximum speed limit that you can operate this motor. But however, in the second case, you have a mechanism to adjust the magnetic field. Usually you operate the machine with the maximum magnetic field that you can allow. Why? Again, we need to go back to those equations that we wrote. You see that the electromagnetic forces that are produced inside the machine also depend on the level of magnetic field. And in operation, you would like to see that you generate the required amount of electromagnetic force by the smallest amount of amperes that you send in, which means that you would like to operate the machine with the maximum magnetic field that the machine is designed to handle. But however, having reached a value of speed that will generate an induced EMF equal to the maximum voltage the machine can withstand, if you now want to go beyond that speed for some reason, usually machines are designed such that the mechanical system, the integrity of the mechanical system is valid for much more than the speed at which the induced EMF is equal to the applied voltage. or induced EMF is equal to the maximum voltage the machine can withstand. You can still go for higher value of speed. And therefore, if you do want to go for higher value of speed, then the only way is looking at this equation. The only way you can do it is by reducing the level of magnetic field, because you cannot violate the condition that the machine can withstand only so much voltage, right? Yeah. See, so let me rewrite those equations here. The generated electromagnetic torque is simply proportional to B multiplied by I. The generated EMF is proportional to B multiplied by omega, right? There is a certain maximum applied voltage the machine can withstand. Let's assume that the machine you have is designed to withstand an applied voltage or a maximum voltage equal to 100 volts. Okay. B, let's say B is equal to 1 Weber per meter square, which then means, for simplicity, I am assuming that EMF is equal to B into omega, and therefore the generated electromagnetic torque is equal to B into I. Okay. Then this means that the maximum speed to which the machine can go is 100 divided by 1, which is 100 radian per second. That is the speed to which you can run the machine. At that speed, how much input amperes it will draw is a separate question, right? Let's not bother about that. You can go up to 100 radian per second. The machine is also designed to take a certain amount of amperes. That also we have seen in the last class, that the maximum size of the conductors inside the machine is, somebody has designed it to be so much. It can take only so many amperes, and let us say the maximum flow of current is I equals 5 amperes. Arbitrarily I am just taking, which now means that maximum speed is equal to 100 radian per second. Maximum torque is equal to 5 Newton meters. Right? Now, this expression says that the developed electromagnetic torque is simply B into I. And for the usage purposes, when I need the machine to develop an electromagnetic torque, I need to send flow of current, right? Now, if I need an electromagnetic torque equal to, let us say, I want to develop 4 Newton meter. I want to develop 4 Newton meter. The question is, how do I do it? I can do it in many different ways. I can say that my value of B will be equal to this much, simply, equal to 2, and then I equal to 2. I can say B equal to 0.5 and then I equal to 8. I can say B equal to 0.25 then I equal to 16. Which combination will you use? In the first machine that we do, you have no option, right? There is simply no option. There is a given B. There is no way of adjusting it. You have to live with whatever B it generates and so much current you have to send. So, first case, this issue doesn't arise at all. This issue arises only in the second case where you have a facility to adjust the magnetic field, right? So, if you have a facility to adjust the magnetic field and you want to generate 4 Newton meter of electromagnetic torque, out of these three, which option will you choose? You will choose the first option going by this, because that results in is less than 5 ampere. That is the least among all these currents, right? But then the issue is that the machine is also designed to withstand only a certain maximum strength of magnetic field. You cannot go beyond that also. And therefore, B equal to 2 Tesla itself is ruled out. This is not possible. We said that B is only equal to 1 Weber per meter square, right? So that option is ruled out. Now, given that, which one will you choose? You will not choose either of the two. You won't choose B equal to 0.5 or B equal to 0.25, because you can go up to B equal to 1, and if you go to B equal to 1, I required is only 4 ampere, right? And therefore, it makes sense for you to operate the machine at the maximum level of flux density or maximum magnetic field strength that the machine is designed for, right? So, you will choose, therefore, under most operating conditions, B is equal to B maximum of the machine, which will then result in I minimum for a required level of torque to be generated. We are not talking about load torque. Load torque you can apply whatever you want, that is an external phenomenon, right? We are only talking about what the motor can generate. Yes. So, there are different restrictions to the level of magnetic field. One is, what is the maximum current that this conductor can take? That is one restriction. Second is, that magnetic field has to flow through this arrangement of the stator, and it has to be flowing through all these regions, everywhere, right? So, if that field has to go through all those regions, you don't want iron to go deep into saturation. So, you need to look at whether the material is going into saturation and whether it can handle that flux density. So, if you require an unnatural level of B, perhaps it may not be feasible to generate it inside that iron arrangement at all, right? So, one has to look at what is the maximum field strength that the geometry can support, and what is the maximum flow of current that can generate that kind of magnetic field. So, all those together has to be considered in order to decide what is the value of B equal to B max, how much it is. So, for a given machine, somebody has designed it and given it to you, then he will then say what maximum flux density you can have, right? And therefore, of course, having designed the machine, he will not say explicitly what is the maximum flux density. He will then say what is the maximum flow of IF that you can allow, because that is what you can do outside, right? For a given IF, machine will generate so much magnetic field. That is by design, right? But however, therefore, there are application requirements where you will need to go beyond the maximum speed of 100 radian per second in this example. Let us now say that you want to go to a speed of 300 radian per second. How do you How can you do that? You can do 300 radian per second. If you look at this equation, you can do 300 radian per second only if you reduce the magnetic field. There is no other go, because the machine cannot take more than that EMF. There are some other elements in the machine which will decide what is the maximum voltage the machine can withstand, and therefore you can go to higher speeds. Higher speeds are possible if magnetic field is reduced. As I said, this is an option available only in the second case. In the first case, where magnets are used, this is not at all an option in this particular machine. Okay? It is feasible if magnetic field can be reduced. However, if you look at electrical power input to the machine, how do you determine that? Electrical power input is applied voltage V multiplied by the flow of current I. You can apply a certain maximum voltage V, and the machine can take a certain maximum input current I, and therefore maximum input electrical supply, that is, this is limited by machine rating, Vmax into Imax. Output mechanical power, which is mechanical, how much is that? Torque multiplied by speed, right? Now, going to higher speeds therefore means that if you want speed to be greater than the rated speed, the machine cannot deliver a mechanical torque that is equal to the rated level of mechanical torque. Let us say that in this condition, we said that the maximum torque that the machine can generate is 5 Newton meter. If you want the machine to still generate 5 Newton meter at a speed equal to a value of 300, you are looking at 1500 watt of output delivered from the machine. Whereas input power is limited. Input power can only be equal to 100 volt multiplied by, how many ampere did we say? 100 into 5. 5 into 100 is only 500 watt input. This is impossible. You cannot supply 500 watt input and get 1500 watt output. So the only way to manage this, if you want to go to higher speed, is to derate the level of mechanical torque the machine can generate. Which means, since we have said that the mechanical torque the machine will generate should be equal to the load torque that is demanded by the load, it only means therefore that if you want to go to higher speed, you must ensure that the load torque applied on the machine is reduced as the speed increases, right? So this kind of operation is called as the field weakening operation. So in field weakening mode, torque that can be allowed to be generated reduces with speed. Note that it is torque that can be allowed to be generated, or I should more specifically say maximum torque that can be allowed to be generated should be decreased as the speed goes on increasing. You can operate the machine with a level of torque that is lower than that maximum torque, that's okay, right? But you cannot go higher than the reduced value of torque, right? So if you then look at a graph that can be drawn between torque capability of the machine and speed. Note that it is torque ability, how much you can allow to be generated. The earlier graph that we drew, this graph speaks about what is the torque that will be generated for a particular value of speed when you apply a certain voltage to it, right? It speaks about a particular operating situation. Whereas now what we are drawing is a different graph that speaks about what is the ability of the machine, maximum ability of the machine to do something. So under that condition, if you say that this is the value of rated speed which is determined by induced EMF consideration, then from 0 to rated speed you can operate in this region with the rated magnetic field. Beyond this region, you have to reduce the magnetic field. Therefore, until this region, everywhere, right? You can supply the machine with the rated flow of armature input current, and since in the first portion you are having the rated value of magnetic field, up to this point the machine is able to generate the rated value of torque. But beyond this point, the machine will not be able to generate the rated value of torque. You will have to derate the machine in accordance with the fact that mechanical torque multiplied by the speed must be equal to a fixed number. And therefore, if you draw a graph of the ability of machine to generate torque versus speed, this graph will be a hyperbola which is determined by the fact that torque into omega is equal to a fixed number. Right? You can operate the machine anywhere inside this graph. So this is the operating region feasible for the machine. Inside this region, where exactly the machine will operate is going to be decided by the actual load that is there, the amount of voltage that you apply and all this. That is determined by the earlier graph. Now, having said all this and having come to an understanding in the last class that armature voltage control is the desirable mode for controlling the speed, and in most cases you don't have a voltage source that is automatically variable, you have only a fixed voltage source available, and from that fixed voltage source you have to generate a variable voltage for running the motor under various conditions. The question is how to do it, and we found that putting a resistance is not the best way to do things. So then the question is what else you can do. So that is where the field of power electronics enters the picture. It is important, therefore, to understand how the philosophy of operation goes. So let's take a simple example that you have a DC source of 100 volts and you want to connect it to a load which is, let us say, a resistor. You want this resistor to be supplied with a voltage of 25 volts DC. This is the goal. Okay. Now, as we said earlier, what can be done is you can simply connect another resistor in series, and you know the value of this resistance. So the other resistor can be very easily determined. A simple law of potential division will tell you what should be the value, but it is a hopeless exercise because it will be highly inefficient circuit. In order to supply so much to this resistor, you will dissipate much more in the other resistor, and it's a useless situation. So now the question is, we need to understand certain things. What you mean by DC? Okay. So let's say you take the voltage across this, and let us say I draw a graph of this with respect to time, and this is the voltage, and this voltage waveform looks like this. So is this DC? Yes, it is DC. No questions about it. It is obviously DC because there is no change in the voltage. Now I draw another graph. Is this DC? Why do you say that? It doesn't change polarity. Okay. Now I draw another graph. Is this DC? It has a component of DC. How do you determine the DC component? Average value of this waveform represents the DC component that is contained in it. So we define DC as a waveform with non-zero DC component. This waveform, on the first waveform, on the other hand, we call it as pure DC. Whereas this waveform is not pure DC, it contains a DC component, but it is also polluted with so many other things. Okay. Now therefore, when I say that I want to supply 25 volt DC to that resistance, the question is what form of DC? Do you require a pure DC, or can you do with some, maybe not so undesirable, but need not be eliminated? So those kind of impurities, whether you can allow, or whether you really need a pure DC. Now, for example, let us assume that you want to supply this DC, right, to some integrated circuit. You have seen IC, everybody? So you want to supply DC to integrated circuit. Now, the requirement of those normally of integrated circuit is that if you see the data sheet, and it says that this IC is able to accept an input voltage of 15 volts, and they will say 15 volts with allowable disturbance limit of 15.1 to maybe 14.9. That is the kind of allowable band that they will have, right? So in such kind of ICs, you cannot allow this kind of huge disturbance that we have drawn in the last graph. So it really means that you require a voltage which is very, very close to pure DC, and that's what you have to live with. You have to generate that kind of supply voltage, high quality DC voltage. Now there may be other systems where if you may want to supply DC, but it can accept all kinds of junk as long as there is a non-zero average value, right? So if you are looking at a resistor, the resistor simply doesn't care. Only thing that resistor is going to do is dissipate electrical power. You really don't care whether it is AC or DC. Resistor behaves the same way to either of them, right? So for a resistor, it's really immaterial. So just for argument's sake, therefore, we are saying that we want 25 volt DC. When we say 25 volt DC, what do we mean therefore? We want the DC part of the waveform that is applied across it to be equal to 25 volt. So this means that the DC component is equal to 25 volt, right? So having understood this, then the question arises, is there a circuitry that I can put in between that gives me 100% efficiency? So now the question arises whether we can have a circuit which you can put in between that gives you 100% efficiency, right? So if you look at elements that you can have in an electrical circuit, you would have seen that circuit elements are, one is a resistor, then you have an inductor, and then you have a capacitor. These are three circuit elements that you are definitely familiar with. You would have seen this in some electrical course, or nowadays it is there in high school physics as well, right? So resistors are denoted by the symbol R, this is L, and this is C. Now of these three elements, which are the ones that have dissipation associated with it? Resistor is a dissipative element, whereas the inductor and capacitor are energy storage elements. So if you send a flow of current I through an inductor L, that flow of electric current generates a magnetic field, and energy is stored in the form of magnetic field. It is not lost. If you reverse the flow of electric, that is I through it, the field that is there decreases and you can get it back. Similarly, if you apply a DC voltage of V across the capacitor, if you apply any voltage of V across the capacitor, half CV squared is the electric field energy that is stored in the capacitor, and if you reduce the supply voltage, you can take that field energy back, right? Whereas in a resistor, if you send a flow of current I squared into R is lost, gone, right? Therefore, if we are looking at a circuit with high efficiency, certainly this is not admissible. You cannot use resistors in the circuit. Now one other element which is there is a switch, right? How do you decide the dissipation in a particular element? Voltage multiplied by flow of current. So voltage across the element multiplied by the flow of current in the element is the dissipation. If you take a switch, the switch may be either on or it can be off. There are no other positions that are there for the switch. So if the switch is on, the voltage across the switch is equal to 0, and some current will flow through the switch, which is decided by the rest of the circuit. Switch doesn't decide how much flow of current will be there. It is just switched it on. other circuit elements will decide how much current will flow through. If the switch is off, flow of current is equal to 0, how much voltage is applied across the switch will be decided by the rest of the circuit, right? But nevertheless, in either case, V into I is 0, right? Whether the switch is on or whether the switch is off, the dissipation across this in the switch is equal to 0 because one of the quantities is 0, which means that in a high efficiency electrical circuit that we want to put in between, the admissible elements are L, C and switch, right? Now we come to the philosophy of how you can design such a circuit. We have said that what we want is a DC component of 25 volts. We are not saying it's a pure DC, and you can use these elements. Therefore, the simplest way one can design this is to put a switch here and then do it. So, how does this give you a DC voltage of 25? What you can do is you operate the switch such that it is on for this much duration and off for this much duration. On, off, on, off. So if you do that, this is switch control. So when the switch control signal is high, we understand that the switch is turned on. When the switch control signal is low, we understand that the switch is off. If this is what happens, what can we say about the voltage across the resistor? This is the circuit. If the switch is on, what is the voltage across the resistor? 100 volts. And if the switch is off, what is the voltage across the resistor? 0. And therefore, the voltage across the resistor will be 100, 0, 100, 0, 100 and so on. What is the average value of this? So this is 1 division and this is 4 divisions, and therefore average value is 1/4 of this. This is 100 by 4, this is 25, right? So we got what we wanted, right? You are having a waveform which has an average of 25 volts, and that's what we want, right? So a simple switch will be able to give you the kind of voltage that is required. But the problem is that if you don't have a resistor, we are talking about DC motors, right? You put a DC motor there, and then let's assume that the DC motor is equivalent to, so let us say that you have this DC source, then you have put a switch here, and then let us say the DC motor is equivalent to an armature resistance and then an induced EMF, some induced EMF here. If this is the model, whether this is the model is a separate question, but if this is the model and you have 100 volt here and you want a voltage of 25 volts at this point, which is what we have designed, and there is a resistance, and this is a DC voltage because the speed is a constant speed, so K into omega will be a constant voltage, and therefore that voltage inside the circle is pure DC. So if that is the case, what will be the waveform of armature input current that flows? So let's say that this is equal to a voltage of 20 volts and my armature resistance is equal to 0.5 ohm. So if I want to draw the waveform of I, how will it look like? Same as the voltage waveform. It will look like this. And what will be this amplitude? 100 minus 20 is 80 into point divided with 0.5 is 160 ampere. This will be the waveform of I. The question is this desirable? Is not desirable. Why? Okay, in this particular case we said earlier that it can take 5 ampere. So let's say that is not the motor and the motor can take 160 ampere. Okay, if motor can take 160 ampere, is this desirable? We want constant current. Why do you want constant current? Motor will generate an electromagnetic torque which is dependent on this waveform. A scaled value of this waveform is the electromagnetic torque, and you don't want to apply this kind of torque to the load. It is a huge ripple torque. You don't know what the load will do, right? Therefore, this waveform is not acceptable. This voltage may be acceptable, right? If this voltage is going to result in this current, then it's not acceptable. If this voltage can somehow be made to result in a smoother current, then it's okay, right? So the question really is not about this voltage that is generated. The question is about what can we do to this waveform. So that we will see in the next class.